describe now. Let's consider I have a link AB. So this is A, this is B, and I have another link of same length L, which is B, C. Same weight and identical link. So this is C. And one end of this link is a hinge, whereas the other end of the link has got a support, which is a roller support, which is on this. Now, this link at its midpoints, D and E, you have this cable. We have this cable, inextensible cable. This is acted upon by the load P at this point, the load P at this point. So now you have to find out what is the relationship between this tension in this cable and the load. That's what is asked. See, you know that if there is no cable DE, what would happen? So this is an inextensible cable. And if this cable is not there, upon action of the load at point B, P load, you would have this static equilibrium is not ensured because you have at this point C roller. So this would be flattened. But the cable present would create tension as this P applied, and hence you get your static equilibrium. So the static equilibrium represented by a coordinate theta, right? So this problems always it's for a single degree freedom. No, it would be very suitable method. Why? Because what do you mean by single degree? If I have one coordinate, independent coordinate to describe an entire geometry of the system, and that is called a single degree freedom system. If it is not constrained or it is one single input required for it. So here I can describe this entire configuration with respect to this angle theta alone. So this is single degree freedom system connected body. And here it's a hinge point A, so I'll consider this as origin. So now the question is determine the relationship between the relationship between the tension T in the cable and the load P at joint at point B in the connected system. So this is the question. So how do you do that? For that, let's apply a virtual work method. Summation of this total work is zero in the system. So here, what are all the external forces? So when I say the tension and P is asked, I should consider that this is cut and I have two forces. One is this, another one is this. So I have here a tension, here a tension. These two are there. Both I should consider, right? Both I should consider. So one is pulling tension force is pulling point D acting at D. Another one is acting at E, I can say. So I have these two forces and this P. And of course, I have a reaction here at right angle at roller that will not participate in the equation. And here A point is a fixed point in the connected system. So though it's having a hinge support, the point will not move from that point. So there is no external force also there. So now here I have this load P and I have a force T at D and force T at E. So my virtual work equation would be like this. So how do I write? Look at force P acting down, so minus P. And where is it acting? At point B. So its virtual displacement is delta YB. So delta yb, how do I write? Since this force is vertically acting down, I have to get this, assume that this point B is given an arbitrary displacement in a vertical direction given by delta yb, and this is virtual displacement delta yb. And similarly, now look at T. So this side T acting at D is to the right, so it's positive T into the coordinate here of point D. The D would be moving along the direction of force, assuming a virtual displacement in this direction. So that coordinate is delta xd. Look at here. I write delta xd here, delta yb. Similarly, look at here. You would say that it would be minus t because the force is to the left, and the virtual displacement required at point E to be considered is delta xe. Why here x I consider is because forces are horizontal. In case I have an inclined force, I will take its component. I will consider for that both x and y displacement. So this is all the three virtual work done. The sum of this work done should be equal to 0 is what is the virtual work principle. So when I make this, I get this. So from this, I can have my relationship between P tension and this. So this is minus quantity taken on the other side. So P into delta YB by here I have delta XD minus delta XD. So this is that relationship. So now here I have to substitute for this virtual displacement. How do I get the virtual displacement? Let's write what are the active forces. Active forces in the first column, and the position coordinate required, and the virtual displacement. I put it in this table form so that it is easy that to work out. So now what are the active force? This force P, and that force is acting down, so minus P. What is the coordinate of point B with respect to this? If this is of length L, this is of length L, AB is length L, I can write that coordinate as YB. And with respect to this point, means this is x-axis and this is y-axis. It's in first quadrant. So point B is in first quadrant and referred by angle theta. So it is L sine theta. L sine theta. So that now what is my virtual displacement? Delta YB would be minus or plus L sine theta. So if I differentiate that, cos theta. So L cos theta delta theta. And now the next active force is T at D, and I require coordinate now XD. Look at I write XD. Why? Because I need delta XD. So horizontal coordinate would be, this is defined by angle orientation theta. So this position would be L by 2 cos theta. L by 2 cos theta. So if I differentiate this delta XD with respect to independent coordinate theta, I'll get this minus L by 2 sine theta del theta, right? And then the next active force is minus T at E. Minus T at E. So I require an XE coordinate. So that would be, how do you get the coordinate there? Simple, see this point position from point O. So this is already from here to here. Midpoint is L cos theta, and this is another L by 2 cos theta. L by 2 cos theta. So I would get this is going to be 3L by 2 cos theta. So this is going to be 3L by 2 cos theta. So delta X G is going to be minus 3L by 2 sine theta del theta. So you had required virtual displacement expressions in terms of differential form of its independent coordinate. So I would, by substituting this in this expression 1, I'll get the relationship. So T equals P into delta YB, that is L cos theta into delta theta divided by delta XD. So delta XD is L by 2 sin theta, that's minus sign here, del theta minus 3L by 2 sin theta del theta. So this minus and minus become plus. So 3L by 2, and here it's minus L by 2. That's going to be L sin theta del theta. So it's going to be P L cos theta del theta by L sin theta del theta. So this goes off. I'll get LL goes out. P cot theta. So what is the relation? So the tension value in the cable is given by P times cot theta. So for the given angular orientation of the link theta and the load value P, I'll know what would be the tension that's created in this frame. Is what can be found out now by a virtual arc method. Any doubt in this, you can ask. Otherwise, we will proceed to solve one more problem, and that ends today's lecture. So you can also have a problem like this, right? So we have seen in this